Hello, welcome back again to this series of lecture. We are now on part 4 on the fundamentals of spectrophotometry. The components of the spectrophotometer includes lamps and laser. They are sources of light. The tungsten lamp is used in visible and near IR spectrophotometry because tungsten lamp provides excellent source of continuous visible and near IR radiation. When tungsten filament is heated, it gives temperature at 3000 Kelvin and it produces useful radiation from 320 to 2500 nanometers. Therefore, this covers the entire visible region and parts of the IR and UV region as well. For UV spectrophotometry, normally it employs a deuterium arc lamp in which an electric discharge or spark causes the dissociation of the deuterium and emits UV radiation from 200 to 400 nanometers. In a typical UV-based spectrophotometer, a change is made between the deuterium and the tungsten lamps when passing through 360 nanometer so that the source with the highest intensity is always employed. So usually we change the source of lamp depending on what region we are going to use. For both visible and UV regions, electric discharge or spark lamps filled with mercury vapor or xenon gas is widely used. The second component of spectrophotometer is the monochromator. We have seen this earlier, that monochromators disperse light into its component wavelength and selects a narrow band of wavelength to pass on the sample or the detector. Monochromator consists of entrance and exit slits, a mirror, and a grating to disperse light. Prisms were used instead of grating in older instruments. So, in older instrument, prisms are usually the component. Gratings, they are reflective or transmissive optical component with a series of closely ruled lines. When light is reflected from or transmitted through gratings, each line behaves as a separate source of radiation. Different wavelengths of light are reflected or transmitted at different angles from the grating. The bending of light rays by a grating is called diffraction. There is some form of what we call stray light, which is wavelength outside the bandwidth. In every instrument, some stray light reaches the detector. Stray light coming through the monochromator from the light source arises from diffraction into unwanted orders and angles and unintended scatter from optical components and walls. Stray light can also come from outside the instrument if the sample compartment is not perfectly sealed. That's why after putting the sample into the cell holder, we make sure that the cover is properly in place. And in some cases, we switch off the light. Entry holes for tubing or electrical wires required at the sample for some experiment should be sealed to reduce stray light. Errors from stray light is most serious when the sample absorbance is high because stray light constitute a large fraction of the light reaching the detector. Stray light in research quality instrument can be from 0.01% to 0.001% or even less. Then, the next component, we have the filters. The filters remove bands of radiation from a signal. The simplest filter is colored glass, which absorbs a broad portion of the spectrum and transmits other portion. Then, we have detectors. Detectors produce an electric signal when it is struck by photons. Example of detectors, we have phototube, which emits electron from a photosensitive negatively charged surface, which is the cathode, when struck by visible light or ultraviolet radiation. The use of spectrophotometer, you can copy this URL of YouTube or you may go back to my channel. So thank you for watching.